In 1850, a mathematician working in Saint Petersburg asked a question so simple a child could ask it. Every equation of motion in physics had two derivatives in it. 2. What would happen, he wondered, if one had 3 or 4? He found an answer, and the answer was alarming enough to close a door, and that door stayed shut for 170 years. Behind it sat the simplest possible theory of quantum gravity. No strings, no extra dimensions, nothing added to the universe at all. Almost everything you have ever heard about 10 dimensions and tiny vibrating filaments exists because that door was locked. Then a graduate student with no published papers and no funding left tried something nobody had thought to try, and the lock turned. So have we just solved quantum gravity? By the end of tonight, you will know exactly what was claimed, exactly what was proven, and exactly what it costs. Get comfortable and let the room go quiet around you. Subscribe if you have not already, and stay with us, because the thing that moved that wall is a single line of arithmetic, and it is small enough that I can show you all of it. Let's dive in. Part 1. The sentence. Nobody expected. The most consequential thing anyone said about gravity last year was said quietly, in an office, by a young man who had every reason to believe he had wasted 4 years of his life. It is September, in Edinburgh. The building is a physics department like any other physics department. Corridors of closed doors, a printer somewhere, whiteboards that nobody quite finishes erasing. Inside one of those offices there is a doctoral student who's been working on the same problem for 4 years and has published nothing. Not a paper, not a short note, nothing. His funding has just run out. He has, by his own account and his supervisor's, arrived at the settled conclusion that he is not going to get a job in physics, and he has more or less made peace with it. His supervisor is privately aware of something worse, which is that the problem he handed this student 4 years earlier was a problem he suspected could not be solved at all, and that anyone watching from outside would have said reasonably that he had killed the young man's career before it started. And on an ordinary afternoon in that condition, no money, no papers, no prospects, the student walks in and says, "I think I know how it works." He's not talking about a small technical detail. He's talking about the thing his supervisor had privately filed under impossible, and what he has in his hands is not a new particle, not a new force, not a new dimension, and not a new equation for the universe. What he has is a very slight adjustment to one of the oldest and most trusted rules in all of quantum mechanics, the rule that takes the mathematics of a quantum theory and converts it into odds, into the actual numbers you would bet on if you were about to run an experiment. He has found a way to write that rule down slightly differently, in a way that gives exactly the same answers everywhere it has ever been tested, and gives sensible answers in one place where it had never been able to give any answer at all. That one adjustment, if it holds, does something to the last 50 years of theoretical physics that is difficult to overstate. Because there are 2 obstacles sitting in the way of the simplest possible theory of quantum gravity, and they have been sitting there so long that most physicists stopped thinking of them as obstacles and started thinking of them as facts about the universe. One of them is a theorem from 1850, a decade before the American Civil War, 75 years before quantum mechanics existed as a subject. The other is an assumption baked into the foundations of quantum mechanics so early and so deeply that for most of a century nobody bothered to list it as an assumption, because it did not feel like one. It felt like the definition of what quantum theory is. Between them, those 2 things closed a door, and the story that filled the space behind that closed door is one you have almost certainly heard, even if you have never read a physics paper in your life. You have heard that gravity does not fit into quantum mechanics. You have heard that the way to make it fit involves strings, tiny vibrating filaments instead of point particles. You have heard that this requires extra dimensions, curled up so small that we cannot see them, and that the number of dimensions is not 4 but 10 or 11, depending on which version you are being told about. You may have heard about membranes, about supersymmetry, about the landscape of possible universes, about the multiverse. All of that is downstream of one claim, which is that quantizing gravity in 4 dimensions cannot be done simply, and therefore has to be done elaborately. The man supervising that student in Edinburgh is Neil Turok. He holds the Higgs Chair of Theoretical Physics at the University of Edinburgh, the chair named after Peter Higgs, who spent his career in that same institution. Before Edinburgh, he directed the Perimeter Institute for Theoretical Physics in Ontario, which is one of the small handful of places on Earth built specifically to think about problems like this one. In May of 2026, he was elected a Fellow of the Royal Society, which is roughly the British scientific establishment's way of saying that whatever this person is doing, it is not a fringe activity. Earlier in his career, he worked with Stephen Hawking. Several of his group's predictions about the structure of the universe have been checked against the sky and found to be right. And here is the detail that makes him worth listening to on this particular question. He used to believe the elaborate story. Not politely, not provisionally, he believed it. His own words are that he used to believe that quantizing gravity required all of that machinery, the extra dimensions, the strings, the membranes, the whole architecture. He is not an outsider who never bought in. He is a convert, which is a different and more interesting thing, because converts have to explain what changed. What changed, in his telling, is that he watched the elaborate story get more elaborate for 40 years without answering any of the questions it was invented to answer, and he is specific about which questions those are, which matters, because there is a version of this complaint that is just grumbling and a version that has teeth. His version has teeth. He names 3 things: what happened at the Big Bang, what goes on inside black holes, whether information is truly lost when something falls into one. Those are the actual problems. Those are the reasons anyone wants a quantum theory of gravity at all. Not for elegance, not for unification as an aesthetic goal, but because there are specific places in the universe where our 2 best theories both apply and cannot both be used, and at those places physics simply stops being able to speak. The first instant of the universe is one of those places. The center of a black hole is another. And the charge Turok makes is that the whole enormous structure built over the last 5 decades has not answered any of them, while becoming steadily harder to check. Then he says something else, and this is the sentence the entire rest of tonight sits underneath. He says, "We claim we understand quantum gravity in a certain limit." Now, if you have spent any time at all around this subject, that sentence should make the back of your neck prickle, because nobody says it. Not people with chairs and fellowships and reputations. The whole convention of the field is that quantum gravity is the great unfinished problem, the thing that eluded Einstein for 30 years, the thing that is spoken about in the future tense. And here is a Fellow of the Royal Society saying, in a recorded conversation, that he and a student believe they understand it, in a certain limit. He does not leave the sentence standing alone, and this is important, because the honest version of this story is better than the inflated one, and the honest version begins here. Almost immediately he adds the caveat himself. We have not solved quantum gravity yet, he says, but we are halfway there. And then, wryly, that halfway is an optimistic way of putting it. So we are going to spend tonight in that gap, between the sentence and the caveat, between a claim that would be the most important announcement in physics since the discovery of the expanding universe, and an admission that the work is unfinished and might not finish. Because the question in front of us is genuinely open, and I want to be straight with you about that from the beginning, rather than leading you along and correcting the record at the end. Have we just solved quantum gravity, or has something smaller happened, something that is not a solution at all, but is in some ways stranger than one? By the end of tonight you will know exactly what was claimed, exactly what was proven, exactly what was not, and exactly what it costs. I am going to lay all of it out in order, including the parts that critics of this work think are wrong, and there are critics, with papers, in journals. But we cannot start with what was fixed. We have to start with what was broken. And the break is older than quantum mechanics, older than relativity, older than the electron. It is older than the idea that matter is made of atoms in the modern sense. To understand what a graduate student did in an office in Edinburgh, you have to go back and watch gravity break physics in the first place. That happened in the 1940s, in the hands of the most famous physicist of the 20th century, and it happened in a way nobody expected because gravity did not resist the new methods. It broke them. Part 2. Why gravity broke physics. The best way to understand why gravity has been such a catastrophe for theoretical physics is to first understand how well everything else went. Start with what a quantum field actually is, because the phrase gets used constantly and explained rarely. Picture space. Not empty space, but space filled with something like an invisible substance that can ripple. It is not a substance in the sense of being made of anything. It is more like a property that space has everywhere, all the time, which is the capacity to vibrate. Now, when that substance ripples, the ripple is what we call a particle. That is the central and genuinely strange idea at the heart of modern physics. A photon is not a tiny ball of light travelling through the electromagnetic field. A photon is a ripple in the electromagnetic field. An electron is a ripple in the electron field. And forces happen because objects trade these ripples back and forth. You push on something by throwing ripples at it, and the ripples carry the push. That picture works. It works so well that it is the most precisely tested idea in the history of human thought. We can calculate certain properties of the electron and match measurement to something like 12 decimal places. That is not a metaphor for accuracy. That is like predicting the distance from Los Angeles to New York and being off by less than the width of a human hair. But there is an awkward truth buried in the framework, and it caused an enormous amount of pain before anybody found a way around it. The awkward truth is this: what a field does at any scale depends on every single ripple it can possibly support. All of them. And there is no smallest ripple. You can always imagine one half the size and then half of that and half again, forever, without limit. So when the first physicists tried to actually calculate something, anything, using this framework, they wrote down a sum, and each term in the sum tried to account for a never-ending continuum of ever smaller ripples. The sums came back infinite. An infinite answer is not a strange answer. It is not an answer at all. If your theory predicts that the mass of the electron is infinity, your theory has not made a bold claim about the electron. Your theory has failed to say anything. Through the 1930s, this was the wall. Some of the best minds in physics thought quantum field theory might simply be wrong, a beautiful idea that did not survive contact with arithmetic. Then, in the late 1940s, 3 physicists independently found the way through. Richard Feynman in America, Julian Schwinger also in America, and Shinichiro Tomonaga in Japan, working in the wreckage of a country that had just been bombed flat, all arrived at essentially the same maneuver. They shared a Nobel Prize for it, and the maneuver is called renormalization. Here is what they realized, stripped of every piece of machinery. The infinite parts of the calculation, the parts coming from ripples too small to ever observe, always show up in the same handful of places. They always end up modifying the same small number of quantities. In electromagnetism, those quantities are the mass of the electron and the charge of the electron, 2 numbers, and we have already measured those 2 numbers. We measured them in laboratories to spectacular precision without knowing anything about the ripples. So instead of trying to calculate them from first principles and getting infinity, you take the measured values, you plug them in, and you let them absorb all the unknowable small-scale nonsense. Once those 2 numbers are fixed by experiment, everything else can be predicted, and the predictions come out finite, and the predictions come out right. At first, this looked like an algebraic trick, like a conjurer's move, cancelling one infinity against another and hoping nobody asks too many questions. Feynman himself was uneasy about it and said so. But over the following decades, physicists came to understand why it works, and the reason is beautiful. Renormalization is a blur filter. It is a way of deliberately smearing out the very smallest features of a field and keeping only their combined effect. And the reason the blurred picture is still an accurate picture for electromagnetism is that in electromagnetism the small ripples have limited influence. The smaller they get, the less they matter to anything you can measure. You can smear them out and lose almost nothing. It is like photographing a landscape at slightly reduced resolution. The mountains are still mountains. That is the framework. And that framework, applied to the electromagnetic force, gave us modern electronics. Applied to the strong nuclear force, it gave us an understanding of what holds the inside of an atomic nucleus together. Applied to the weak force, it explained radioactivity. 3 of the 4 fundamental forces of nature yielded completely. Gravity did not. And the reason gravity did not is not that gravity is complicated. In some ways, gravity is the simplest of the 4. The reason is that gravity is a different kind of thing. Every other field is a field that lives in space. The electromagnetic field is spread through space the way a mist is spread through a valley. But the gravitational field, according to Einstein, is space. Or more precisely, it is space-time, and gravity is what you experience when space-time is curved and you follow the curve. When Einstein rewrote gravity in 1915, he did not describe a force pulling objects across a stage. He described the stage itself bending and objects following the bend. That is why the moon goes around the Earth, not because the Earth reaches out and grabs it, but because the moon is coasting in a straight line through a region where straight lines curve. So when you go to quantize gravity, the rippling thing you are quantizing is not something inside space, it is space. And that turns out to change the arithmetic entirely. Feynman tried it. He worked on this personally, along with a physicist named Bryce DeWitt, who spent much of his career on it. And what they found was the exact reverse of the electromagnetic case. In gravity, the tinier the ripple in space-time, the more it matters. Not less, more. The small stuff does not fade into irrelevance. It screams. Every microscopic wrinkle in the fabric influences the larger wrinkles in innumerable subtle ways, and those influences cannot be gathered up and hidden inside a handful of measured numbers, because there is no handful. There is an endless list of them. The blur filter fails. You smear out the small features and the picture you get back is not the landscape. John Donohue, a quantum field theorist at the University of Massachusetts Amherst who has spent years on this exact question, puts it with no drama at all. Everyone was concerned about this, and this is the reason quantum general relativity was considered a problem. I want to be careful here, because there is a lazy version of this story that says gravity and quantum mechanics are incompatible, full stop, and that is not quite right. You can absolutely do quantum calculations with gravity, as long as you are content with approximations valid at ordinary energies. That is done routinely. What you cannot do is push the calculation down to arbitrarily small scales and have it remain meaningful. The technical word is that quantized general relativity is not renormalizable, and what non-renormalizable actually costs you is worth stating plainly, because it is the whole reason this matters. A renormalizable theory is one where you are allowed to be ignorant about the small scales. You can admit you do not know what the universe is doing at a billionth of the size of a proton, and still make confident predictions about the things you can see. That permission is what makes physics possible at all. It is why you can build a bridge without knowing what quarks are doing. A non-renormalizable theory revokes that permission. It demands that you understand every layer of reality at once, all the way down, before you can say anything reliable about the bottom. And nobody has ever managed to understand every layer of reality at once, because it is not obvious that there is a bottom. That is why, when someone asks what happened at the Big Bang, the honest answer from physics has been silence. Not because nobody has thought about it, because at the first instant both of our great theories apply with full force, and the moment you put them in the same sentence the equations stop returning numbers. The question is not hard. The question is currently unaskable. Same with the center of a black hole. Whatever is at the middle, our description of it consists of the word singularity, which is not a description of anything. It is a note in the margin recording where the mathematics gave up. That was the state of things by the mid-1970s. 3 forces tamed, 1 force refusing, and a growing sense that gravity was going to require something genuinely new. And then a graduate student found the way through. Exactly one way. He was able to show it was the only way. And it worked. And it made gravity look almost exactly like the forces we already understood. It should have been one of the great moments in the history of the subject. Instead, it was quietly buried for 40 years, including by the man who found it. Part 3. The Sweet Little Scalar and the Ghoul. In the middle of the 1970s, a graduate student at Brandeis University named Kellogg Stell sat down with the problem everybody had given up on and found the only door in the room. His paper came out in 1977 in Physical Review D, and to explain what he did, I need to show you one equation without writing it down. Einstein's theory of gravity, when you write it in the compact form that theorists prefer, is astonishingly short. It contains a term for the curvature of space-time, and it contains a scale, a number that tells you how strongly matter bends geometry, which you can express as Newton's constant, or as a length, or as a mass, and physicists call that length the Planck length, and that mass the Planck mass. Those are all the same piece of information wearing different clothes, and then, optionally, there is a term with no derivatives at all, which is the cosmological constant, the thing driving the universe apart. That is essentially the whole of general relativity, one curvature term and a scale. Now the curvature term contains 2 derivatives, because curvature is built out of how the geometry changes, and then how that change changes. 2. And Stell asked the obvious question that nobody had properly followed through. What if you add the next thing? What if, alongside the curvature, you also include terms that are the square of the curvature? That sounds like an arbitrary thing to do until you notice what it does to the shape of the theory. Because squaring the field strength is exactly how every other force in nature is written. Maxwell's electromagnetism is built from the square of the electromagnetic field strength. The theory of the strong nuclear force is built from the square of its field strength. That is the standard form for the kind of theory physicists know how to quantize. So putting the curvature squared into the gravitational action makes gravity look, structurally, like the forces we had already conquered. It stops being the odd one out, and the arithmetic changes in exactly the way you would want. Remember the problem. In ordinary gravity, the smaller the ripple, the more it matters, which is what breaks the blur filter. The curvature squared terms suppress the smallest ripples. In technical language, the behavior of the gravitons propagator at high momentum improves from 1 over momentum squared to 1 over momentum to the 4th power, which sounds like bookkeeping and is in fact the whole game. It means that as you go to shorter and shorter distances, the contributions get quieter instead of louder. The small stuff fades. The blur filter starts working again. Stell proved that the resulting theory is renormalizable, a quantum theory of gravity in 4 dimensions, in ordinary space-time, with no extra dimensions, no strings, no membranes, no supersymmetry, nothing added to the world, and the infinities can be absorbed, and finite predictions come out the other end. There is one more feature that makes this more than a clever construction, and it is the feature that gives this whole story its peculiar flavor. The symmetries of general relativity only permit 2 such squared terms. 2, not a family of them, not an adjustable menu. Exactly 2 independent combinations exist, and they have names. One is built from the Ricci scalar, which you can think of very roughly as measuring how volumes get distorted, and the other is built from the Weyl curvature, which measures how shapes get distorted while volumes stay the same. That is it. So the theory Stella wrote down is not one choice among infinitely many. It is essentially forced. Given that you want a local theory of gravity in 4 dimensions that is renormalizable, this is what you get. There is no design freedom. Stell's own summary of what he had accomplished is the flattest sentence you will ever hear a physicist use about a major result. He said, "That gives you a indefinite article, quantum theory of gravity." And then, of course, the question is, do you like it? Do you like it? Hold on to that question because we are going to come back to it, and by the time we do it will have changed meaning entirely. Because the answer, for almost everybody, including Stell himself, was no. And the reason is that the enhanced fabric of space-time he had built could now support 3 different kinds of ripple instead of 1. The first is the ordinary graviton, spin 2, the quantum of the gravitational wave, the particle everybody expected and wanted. Fine. The second comes out of the Ricci part of the new machinery, and it is a scalar particle. Physically, it corresponds to the local scale of the metric, very loosely to how much space itself is stretched or shrunk at each point, without any preferred direction. Stell, in a phrase I love, called it a sweet little scalar. It is harmless. It is more than harmless, actually, and we will see later that it may be the most important object in this entire story. The third comes out of the Weyl part, and the third is a monster. It is another spin 2 particle, but it arrives carrying a minus sign that does not belong there, and that minus sign is not a cosmetic detail. It means the particle has negative energy. Think about what negative energy implies. Normally, to make a particle, you have to pay for it. You put energy in and you get a particle out. This one is the reverse. Space gains energy by producing it. So the vacuum should be able to make them for free and then make more and more because every one it makes leaves it richer than before. Empty space should whip itself into an increasingly violent inferno, spontaneously, for no reason, forever. And there is a second problem, worse in a way, because it is not a problem about stability but about meaning. In the standard way of doing the calculation, events involving this third particle can come out with a negative probability. Not a small probability, not a strange probability, a negative one, probability of minus 0.3. That is not a surprising result about nature. That is a sentence with no content, like a length of minus 4 meters, or a Tuesday that happened twice. Physicists have a word for particles like this. They call them ghosts, and they have a word for theories that contain them, which is that such theories are sick. So that was the situation in 1977, a unique, renormalizable, 4-dimensional quantum theory of gravity requiring nothing new in the universe, haunted. Now, over the next decade, 2 more results came in that made the whole thing more tantalizing rather than less. In 1981, Efim Fradkin and Arkady Saitlin argued that this theory of gravity is asymptotically free. In 1985, Ivan Avramidi and Andrei Bavinsky established the result more completely in a paper in Physics Letters B. Asymptotic freedom is a property with a track record. It is the property that made the strong nuclear force understandable, and the physicists who discovered it there won a Nobel Prize. What it means is that as you probe shorter and shorter distances, the strength of the interaction runs down towards 0. The theory gets simpler the deeper you go. At extremely short distances, it becomes almost trivial. Barely interacting waves, nothing blows up. Nothing needs rescuing by some deeper theory, because there is no scale at which it stops making sense. Take a moment with that, because it is the part people skip. A theory that is both renormalizable and asymptotically free is in principle complete. Not complete in the sense of describing everything in nature, complete in the sense that it does not hand you a bill you cannot pay. It does not break down. It does not need to be embedded in something larger. And in 2024, John Donoghue and his collaborators found a related result about what happens when gravitons in this theory smash into each other. The more violent the collision, the weaker gravity becomes, which suggests, as Donoghue put it, that the theory never breaks down, and could in principle take you all the way to the deepest levels of reality. He then added, with a discipline that makes him worth quoting, that he is not convinced this is the final theory. But it could allow it to be one. So why did nobody build on it? Partly the ghost, but partly something much more human and much more accidental. Almost immediately after Stell's paper, physicists stumbled onto a different approach called supergravity, which proposed that every known particle has an undiscovered partner particle, and which appeared to solve a whole cluster of problems at once. Supergravity was thrilling. It captured the field's imagination completely, including Stell's own. It would go on to merge with string theory, and together they would dominate theoretical physics for 4 decades. Against that, a theory with a negative energy particle in it and no obvious way to remove it could not compete. It did not get refuted. It got outmarketed. For decades afterward, Stell's paper was cited about 10 to 20 times a year. In a field where thousands of papers appear annually, that is not obscurity exactly, but it is close. It is the citation rate of something considered a historical curiosity, a thing you mention on your way to talking about something else. And I want to sit with Kellogg Stellar for a moment, because his life is the emotional shape of this entire subject. He was a young man when he found the only known way to write a renormalizable quantum theory of gravity in 4 dimensions without adding anything to the universe. It is not an exaggeration to call that one of the more remarkable single results of 20th century theoretical physics. And he did not like it. He said, when interviewed decades later, that he had been aware that not everything was going to be hunky-dory about this. He never came back to work on it. He spent his career at Imperial College London on other things for decades, and he watched from a distance as interest in his abandoned theory slowly, quietly began to return. He called the revival agreeable. He said his own reaction to his theory was that it might be a possible link, a kind of intermediate regime, a layer of reality rather than the bottom of it. He died in October of 2025. By then his paper was being cited more than 150 times a year, which is roughly 10 times the rate it managed during the decades when he was alive and working and might have done something with it. He found the door. He looked into the room, decided he did not like what was in there, closed it, and lived long enough to watch other people walk in. Which brings us to what exactly was in the room. 2 objections buried this theory. We are going to take them one at a time, and we are going to start with the older one. And it is older by a very long way. It is not from the era of quantum mechanics. It is not even from the era of electricity as a practical technology. It comes from a man working in Saint Petersburg in 1850. Part 4. The oldest no in physics. There is an argument in physics so old that when it was made nobody knew what an atom was, nobody knew what an electron was, and the fastest way to send a message across a continent was a horse. The year is 1850. The place is Saint Petersburg. The man is Mikhail Ostrogradsky, a Ukrainian-born mathematician working in the Russian imperial capital, and he is doing something that mathematicians of that era did constantly, which is taking a beautiful piece of recent work and asking what happens if you push it. The recent work belonged to William Rowan Hamilton, who had reformulated the whole of classical mechanics in terms of energy. Hamilton's version of mechanics is why we still talk about the Hamiltonian of a system when we mean its energy written down as a function of positions and momenta. It was, and is, one of the great reorganizations of physics, the same content as Newton, but arranged so that its structure is visible. And Ostrogradsky asked a question so simple it sounds naive. Newton's law, in the form everybody learns, says force equals mass times acceleration. Acceleration is the second derivative of position, the rate of change of the rate of change. Two derivatives. Every fundamental equation of a motion anyone had ever written had two. So Ostrogradsky asked, what if it were 3, or 4, or 17? Is there anything actually wrong with an equation of motion that contains more derivatives than 2? Or is that just a habit? He found something, and what he found has been used as a weapon ever since. He showed that if the equations of motion contain more than 2 derivatives, in a way that cannot be quietly integrated away, then the energy of the system, the Hamiltonian, is what physicists call unbounded below. There is no floor. There is no lowest energy state. You can find configurations of the system with arbitrarily negative energy, as negative as you like, without limit. I want to make sure that phrase lands because it sounds abstract and it is not. The reason anything in the universe is stable is that it has a lowest energy state and it settles into it. A ball in a valley rolls to the bottom and stops. An atom has a ground state, and that is why matter exists rather than continuously collapsing into something smaller. Water runs downhill and eventually reaches the sea, and the sea does not keep going. Every stable structure you have ever seen, a rock, a tree, your own body, is something that found a bottom and sat in it. Ostrogradsky's higher derivative systems have no bottom. There is always further down, and there is a specific mathematical fingerprint that tells you when you are in trouble. The energy of such a system depends linearly on one of the momenta rather than on its square. That linear dependence is the crack in the floor. The excitation associated with it now carries a name that physicists use with a certain amount of dread. It is called the Ostrogradsky ghost. Let me show you why everybody found this decisive, because it is easier to feel than to argue. Imagine you are standing in an ordinary room. On the table in front of you is an ordinary object, a paperweight, say, obeying ordinary physics, the kind with 2 derivatives. Now imagine that beside it I set down a small device, whose internal workings obey a 4-derivative equation of motion. It looks like nothing, a little brass cylinder, and I connect it to the paperweight with a wire so that the two can exchange energy, which is all that any 2 physical systems in contact ever do. Watch what happens. The device has no lowest energy state, so it can always find a configuration further down, and it will, because there is nothing stopping it. And every unit of energy it sheds on the way down has to go somewhere. It goes into the paperweight gets hotter, the device drops further and gives up more energy, and the paperweight gets hotter still and the device keeps falling, because it can always keep falling. There is no bottom to reach. The room warms, then the room glows, then the walls are radiating and the air is a plasma and the whole thing is running away, and the device is still falling, still handing over energy, and nothing in the mathematics ever says stop. Now look up from the table and look at the universe. It is not doing that. The room you are in is not doing that. Space is not filling with free energy from an inexhaustible source. Whatever nature is made of, it is not made of that. That is the argument. It is not a subtle argument, and it does not need to be. Higher derivative equations of motion appear to describe an object that could not coexist with anything else in a universe. Ostrogradsky's result is often described as the single most powerful restriction on fundamental interacting continuum field theories, more restrictive than almost anything else we know, and it is arguably the oldest no-go theorem in physics, which means it has been standing for something like 176 years, which is longer than the lifetime of anyone who ever taught anyone who taught anyone currently working in the field. Here is the part I find genuinely poignant. Physicists kept trying anyway. They kept trying because higher derivatives are irresistibly useful. Remember why. Extra derivatives tame infinities. They make sums converge that otherwise diverge. And in the middle of the 20th century, when the infinities of quantum field theory were the central scandal of the subject, that promise was extremely difficult to walk away from. Homi Bhabha, the Indian nuclear physicist whose name is now on India's principal atomic research centre, worked with higher derivative field theories in the era when everybody was throwing models at the nuclear force to see what stuck. Werner Heisenberg, who had helped invent quantum mechanics in the first place, played with them too. As far as anyone can tell, Baba may have been the first to seriously try building a quantum field theory this way, and their motivation was exactly the one that would later make four-derivative gravity renormalizable. They thought higher derivatives would make the theory more convergent, would reduce the infinities, would make the arithmetic behave. They were right about that. That is the thing. They were completely right about the benefit. The instability was simply the invoice attached to it, and it always arrived, and it was always too expensive. So a pattern set in, over more than a century, in which higher derivative theories were the fruit on the high branch. Everybody could see why you would want them. Everybody knew what happened when you took one. There is one more feature of Ostrogradsky's theorem that matters enormously for where we are going, and it is a piece of fine print rather than a headline. The theorem is a statement about non-degenerate systems, systems where the higher derivatives genuinely add new independent freedom and cannot be shuffled away by clever rewriting. There are known exceptions. If your system is degenerate in the right way, the argument does not apply. Physicists working on modified theories of gravity have spent years hunting for exactly these loopholes, and some have been found. But the general expectation stood, and it stood firmly. Write down a higher derivative theory, and you will find it is unstable, in general, with exceptions that have to be earned. There is also a subtlety about the shape of the disaster that we are going to need later, so let me plant it now. Everything I have just described is classical. It is the story of an object with no lowest energy state, sliding downhill forever, dragging the rest of the world along with it, the runaway on the table. But when you take a higher derivative theory and quantize it, the trouble changes costume. It does not show up as an object falling forever. It shows up somewhere far stranger, in the mathematics that describes what states the system can even be in, and it wears a different name. So there are really two objections here, not one, and they are not the same objection in different words. The classical one is about stability. The quantum one is about meaning. Both of them have been used to close the same door, and they have to be dealt with separately, because a fix for one does nothing at all for the other. That is why this took so long. Everyone who came to this theory hoping to rescue it had to get past two independent walls, built a century apart in different materials, and for 170 years nobody got past either. Which raises a question that, in hindsight, is almost embarrassing. For 170 years, physicists applied this argument to higher derivative theories of every kind, and gravity was one of the theories they applied it to. But gravity is not like the other theories. Gravity is the one where energy behaves differently from everything else in physics, where the very definition of the energy of a system is contested, where energy is not local in the way it is for every other field, where you can have a system whose total energy is zero while it contains stars. Everybody working on this knew that about gravity. It is in the textbooks. It is in the first chapter of the textbooks. And for a very long time, nobody stopped to ask whether the 1850 argument, built by studying mechanical systems in a fixed and unchanging space, was even the right argument to apply to a theory in which space itself is the thing doing the moving. Somebody finally asked, and the answer turned out to be sitting in front of us the entire time, printed across the whole sky, visible on any clear night, in the one feature of the universe that every person listening to this already knows. Part 5, The Disaster, was in the description. Let me put the first objection in its strongest form, so that when it comes apart you can see it come apart honestly, rather than being talked out of it. The objection is that a four-derivative theory of gravity has an energy with no flaw, which means it should be violently unstable, which means it cannot describe the universe we live in, because our universe is manifestly not tearing itself apart. That is the argument. It has been considered decisive since 1850, and the way you break it is not by finding an error in Ostrogradsky's mathematics, because there is no error in Ostrogradsky's mathematics. You break it by noticing something about the subject matter. Here is the first thing to notice, and it is so elementary that it is almost always taught in the first year of a physics degree, and then never thought about again. Gravitational energy is already negative. Take the Earth going around the Sun. The Earth has kinetic energy, because it is moving, about 18.5 miles every second, which is fast enough to cross the United States in a little over 2 minutes. That kinetic energy is positive. But the Earth also has gravitational potential energy with respect to the Sun, and that quantity is negative. It is negative because of how we define it. An object infinitely far away, at rest, is defined as having zero gravitational energy, and anything gravitationally bound to anything else has less than that, less than zero. To pull the Earth free of the Sun forever, you would have to put energy in, which means it currently sits in a hole. That is not exotic physics, that is bookkeeping. But look at what it implies about the intuition we were using a moment ago. The intuition that energy must have a floor, that stability requires a bottom, that negative energy is a red flag. That intuition was built by studying things sitting in a fixed space, balls in valleys, atoms with ground states, water finding the sea. Every one of those examples is a system in space, and for systems in space the intuition is excellent. Gravity is not a system in space. Gravity is what space does. And in gravity, physicists have been perfectly comfortable with energies that are not positive for over a century because they have no choice. The potential energy of every bound system in the universe is negative, and if you take a large enough region and add everything up, the total can come out at essentially zero even though the region contains galaxies. Whatever intuitions we have about energy needing a floor, gravity has been quietly ignoring them the whole time. Now here is the second thing to notice, and this is where the argument does not just weaken but inverts. The universe is expanding. You know this. Every galaxy outside our local neighborhood is receding from us, and the further away it is, the faster it goes. And it is not merely expanding, it is accelerating, which is the observation that won a Nobel Prize and which we currently attribute to the cosmological constant, or dark energy, or whatever the right name turns out to be for the thing pushing space apart. If that constant is what it appears to be, then the expansion is not slowing and will not slow. It is exponential, which means that some fixed span of time from now, every distance will have doubled, and after the same span again it will have doubled again and again without end forever. Sit with that in the vocabulary of the physicist analysing stability. When you ask whether a system is stable, you nudge it and see whether it settles back or whether it runs away. And a quantity that doubles and doubles again and keeps doubling without limit is not a settling system. Exponential runaway is the textbook signature of an instability. It is, essentially exactly, what the Ostrogradsky problem looks like from the outside. So when Turok's group went back to the four-derivative theory of gravity and did the analysis properly, not as a generic mechanical system with extra derivatives bolted on, but as a theory of gravity, using the tools you would actually use on a gravitational theory, they found that the Ostrogradsky instability in this theory is nothing other than ordinary gravitational expansion. That is the claim. The monster in the mathematics is the expansion of the universe. It is not an additional pathology sitting alongside cosmology. It is cosmology, described in a vocabulary that makes it sound like a catastrophe. And when you analyse that expanding solution, the way you analyse the expanding solution in Einstein's own theory, the way cosmologists have been doing routinely for the better part of a century, it is absolutely stable. Not marginally stable, not stable under conditions, stable. There is a detail about how this resolution came to light that I find telling. In the conversation where Turok first laid this out publicly, the interviewer, someone who had been reading the relevant papers closely and had come prepared with a careful summary of the two horns of the objection, stopped and said that he had not known that part. He had the second horn mapped out in detail, because the second horn is the famous one, the one that gets argued about in the literature. The first horn, the one that had supposedly been fatal since the middle of the 19th century, had already been quietly dismantled by rereading it as cosmology, and the news had not travelled. That is how these things actually go. There is no announcement. Somebody redoes an old calculation in the correct setting, the monster turns out to be furniture, and it takes years for anyone outside the room to notice. I want to flag how quietly enormous that is. One of the two objections that closed off the simplest possible route to quantum gravity, an objection older than the theory of evolution by natural selection, was an artifact. Not a mistake in anybody's algebra. Something subtler and more embarrassing than a mistake. A correct theorem, correctly proved, applied to a system it was not built to describe, by people who had every reason to think the application was harmless. The runaway existed in a language, not in the sky. That is worth saying plainly, because it is the shape of this whole story, and we will meet it again before the night is over. The disaster was in the description, not in the world. There is something almost funny about where that leaves you, and it is the kind of funny that keeps you awake. The reason people said this theory could not describe the universe was that it predicted a runaway expansion which would be visible from any point inside it, and the universe is undergoing a runaway expansion which is visible from any point inside it. We have known that since the 1920s for the expansion, and since the late 1990s for the acceleration. The objection was, in a sense, the observation. Nobody put the two side by side because they were filed in different drawers, one in the drawer marked mathematical pathology, and the other in the drawer marked cosmology. You are living inside the instability. It is doing the only thing it has ever done, which is to carry everything gently away from everything else at a rate you cannot feel, and it has been doing that for something like 13.8 billion years without incident. When you look up at a dark sky and see the light of galaxies that are moving away from you, you are looking at the disaster. It is very quiet, and there is a consequence of this that is easy to miss and worth holding on to, because it changes how you should hear the rest of tonight. If the classical instability of a four-derivative theory of gravity simply is cosmic expansion, then the theory was never describing a universe that destroys itself. It was describing a universe that gets larger. Those two things look identical in the equations and are not remotely the same experience from the inside. One of them is the end of everything, the other one is Tuesday. The entire difference between them lives in whether you remembered that you were doing gravity when you wrote the mathematics down, and for 170 years the field kept forgetting, so one horn is down. But I have been careful all along to say that there are two objections, not one, and the second is not a smaller version of the first. It is a different kind of thing entirely, and it cannot be dissolved by pointing at the sky, because it is not about stability at all. It is about whether the theory means anything, and to get to it we have to take a detour that will feel, at first, like a detour into pure mathematical convenience, into a trick that physicists have used for 80 years, that works so well nobody questions it, and that has one hidden cost. The cost is that the trick works in a version of time that is not the version of time you're living in. Everything good anyone has ever said about this theory of gravity was said about that other time, and the return journey, from that time back to ours, is where both of the disasters have always been waiting. Part 6. Real time, imaginary time. Everything good. I have told you about this theory of gravity comes with a piece of fine print, and the fine print is not a technicality. It is the hinge of the entire 50-year story. Renormalizable, asymptotically free, under control at short distances. Every one of those results was established in a version of the theory that lives in imaginary time. I need to explain what that means, and I want to do it without any machinery, because it is one of the most elegant ideas in physics, and it almost never gets explained to anyone outside the subject. Quantum mechanics, in the formulation Feynman gave it, works like this. If you want to know the probability that a particle gets from here to there, you do not find its path. You consider every path it could conceivably take, the straight one, the loop out past Jupiter, the one that goes backwards for a while, and you assign each of them a contribution, and you add all the contributions up. That sum is called the path integral, and it is the deepest way anyone has found to say what a quantum theory actually is. The particle does not choose a route. Every route contributes, and what we see is the total. Now, the contributions are not simple numbers. Each one carries something like a phase. Think of it as a little arrow pointing in some direction, and the direction depends on the path. To add up the contributions, you add up the arrows tip to tail, and the answer is how far you have travelled from where you started. And here is the crucial behaviour. Paths that are wildly different from the sensible one have arrows pointing in wildly different directions, so they mostly cancel each other out. That cancellation is why the world looks classical. The straight path survives because its neighbours agree with it. That is lovely as a piece of physics and a nightmare as a piece of arithmetic, because in real time that sum oscillates. The arrows spin around faster and faster as the paths get stranger, and if you try to compute the total directly, you're attempting to add up an unlimited number of terms that are violently cancelling against each other, and the answer you get depends terrifyingly on exactly how you do the adding. It is not merely difficult. It is the sort of problem where a computer will hand you back noise and no warning. So physicists use a trick, and it is one of the great tricks. You rotate time, not physically, so mathematically. Time appears in these equations as a number, and you allow that number to become imaginary. You give it a quarter turn, off the real axis, into the imaginary direction, and when you do, the oscillation vanishes. The spinning arrows stop spinning. Every contribution that used to oscillate now simply decays exponentially, so that strange paths contribute less and less instead of cancelling chaotically. The impossible sum becomes a well-behaved, convergent, perfectly calculable sum. It is like turning a screaming feedback loop into a soft hum by adjusting one dial. This is called the Wick rotation, and I want to be clear that it is not a cheat and it is not obscure. It is how essentially all serious non-perturbative work in quantum field theory is done. It is how we compute the properties of the strong nuclear force. You put the theory on a lattice, a grid of points in imaginary time, and you let a supercomputer add up the configurations, and out come the masses of particles that match what accelerators measure. Some of the most impressive quantitative successes in modern physics live entirely in imaginary time. Nobody apologizes for it. It is worth pausing on how much of what we consider settled knowledge was obtained this way, because it affects how seriously you should take results proved in imaginary time. The mass of the proton is not something anyone can calculate on paper. The strong force binds so tightly at ordinary distances that every approximation scheme collapses. What physicists do instead is lay down a grid, a lattice of points, in imaginary time, and have a computer sample enormous numbers of possible field configurations on that grid, weighting each one by how much it decays. Out the other end come numbers, masses of particles, properties of matter under conditions that exist only inside collapsing stars. Those numbers match measurement. The whole enterprise rests on the quarter turn, and it works. Whatever is happening when you rotate time into the imaginary direction, it is not a fudge, and it is not a fiction, because fictions do not predict the mass of the proton. Imaginary time also has a distinguished history in gravity specifically. Stephen Hawking built much of his most famous work on it. His derivation of the temperature of a black hole, the result that connects gravity to thermodynamics and gave us the idea that black holes evaporate, comes out of treating the geometry in imaginary time and noticing that it closes up smoothly. His proposal about the beginning of the universe used the same move, rounding off the sharp point at the start of time by rotating into the imaginary direction, so that there is no edge, no first moment, nothing to have a cause. So this is not an exotic tool that one group is leaning on. This is a central technique of 20th century theoretical physics, and Turok worked directly with the man who did more than anyone to make it respectable. The rotation does not work well with Einstein's theory of gravity. People have tried, and the Euclidean version of general relativity has famous pathologies of its own. But, and this is why the curvature squared terms keep pulling people back, those extra terms suppress curvature at short distances, and once you have them, the rotated theory looks sensible. In imaginary time, four-derivative gravity behaves. That is where the renormalizability lives. That is where the asymptotic freedom lives. That is where all the good news has always lived. And then you have to come home. We do not live in imaginary time. You're not experiencing a quarter turn off the real axis. You are experiencing Tuesday, in order, 1 second at a time. So having done the calculation in the convenient world, you have to bring the answer back into ours, and that passage has a name, analytic continuation, and it is the most dangerous step in the entire procedure. Not because the mathematics is hard, although it is, but because things that were perfectly well behaved on one side of the rotation can arrive on the other side carrying problems that were invisible before. That is exactly what happens here. Both disasters strike in the return trip. I think this is the single most underappreciated fact about the 50-year history of this theory, so let me state it as plainly as I can. Nobody ever found anything wrong with four-derivative gravity in imaginary time. The theory is, as far as anyone can tell, entirely healthy there. Controlled, calculable, complete. The objections that buried it are not objections to the theory. They are objections to what the theory turns into when you rotate it back into the world where clocks tick forward. And that is why people kept coming back to it. Over 4 decades, physicists would wander back, poke at it, and wander off again, because the virtues were too specific to forget. There is no other candidate with this combination of properties: unique, local, four-dimensional, renormalizable, asymptotically free, requiring nothing new in the universe. When something is the only member of its category, the field does not forget where it lives. It just keeps a respectful distance. So we come now to the second wall, and unlike the first one, this wall is not about whether the universe would tear itself apart. It is about something more fundamental and much harder to shrug off, which is whether the theory means anything at all, whether the numbers it produces can be understood as answers to questions about the world. The objects standing on top of that wall have a name that physicists chose more than half a century ago and never regretted because it fits. They are called ghosts, and the standard argument about them, repeated in textbooks and lectures and review articles for generations, contains an error so basic that once you see it, you will wonder how it survived. Part 7. Ghosts. Let me step back and put the pieces we have on the table together, because we are exactly halfway, and the picture is already stranger than the version most people carry around. There exists a theory of gravity, written down in 1977, that is unique, not one option among many, but the only local four-dimensional possibility. It is renormalizable, which no other theory of gravity in ordinary spacetime is. It is asymptotically free, which means it never breaks down at short distances and never needs rescuing by something deeper. It requires no strings, no extra dimensions, no supersymmetry, no new structure in the universe whatsoever. Two objections stood in its way. The first one, dating from 1850, turns out to be a description of ordinary cosmic expansion wearing a frightening costume, and every good property the theory has was established in imaginary time, which is where all serious calculations in field theory live, so that is not a complaint either. Which leaves one thing standing between the simplest possible theory of quantum gravity and the world. In the quantum version of the theory, the space of possible states does not behave the way you were taught it must. And to see why that matters, I have to teach you one piece of vocabulary, gently, because it is the whole ball game. In quantum mechanics, the state of a system is described by an object that behaves mathematically like an arrow, a vector, in an abstract space, not physical space, a space of possibilities, and like any arrow, it has a length, or more precisely a length squared, which physicists call its norm. In every version of quantum mechanics anyone learns, that norm is positive. It has to be positive. In fact, the standard setup insists that you scale every arrow so that its length is exactly 1, and this normalization is woven so deeply into the subject that you meet it in the first week and never question it again. The space of states, with all lengths positive, is called a Hilbert space, and if you ask a physicist what quantum theory is, somewhere in the answer will be the phrase Hilbert space, said the way you might say water is wet. In a four-derivative theory, some of the arrows have negative length squared. Those states are what physicists call ghosts, and the standard argument, which you will find repeated in many places in the literature and in the mouths of many extremely competent people, runs like this. A negative norm corresponds to a negative probability. Negative probabilities are meaningless. Therefore the theory is unphysical. Therefore we are done here. Turok's claim, and Bateman's, is that the middle step of that argument is simply false. Here is the reasoning, and I would like you to notice that it does not require any mathematics at all. A quantum state is a label. It is a bookkeeping device that we attach to a system in order to compute things about it. It is not the system, and its norm, the length of the label, as is not an observable quantity. There is no experiment you can perform, even in principle, whose outcome is the length of a state vector. You cannot put a state vector on a scale. What you can observe are probabilities of transitions. You set something up, you measure it later, and you record how often you get each outcome. Those are the numbers physics is answerable for. The norm is scaffolding. Turok has an image for this that I think is the best single line in the whole story. He says you can have a red dancing unicorn in your equations, and if it is unobservable, it actually does not matter. There may be another set of equations with exactly the same observable content and no unicorn in them. You do not see it in the lab, so who cares? Now, if you want an intuition for how a space can have negative lengths in it without anything being broken, you do not have to go anywhere exotic. You're sitting in one. The space-time described by relativity has exactly this structure. When you measure the separation between two events in space-time, the quantity that all observers agree on, the interval, can come out positive or negative or exactly zero, depending on whether the two events are separated more in space than in time, more in time than in space, or in the precise balance that a light ray traces. Physicists call those cases space-like, time-like, and null. One family of separations carries the opposite sign from the other, and nobody in the history of the subject has ever concluded from this that space-time is inconsistent or unphysical, because there is nothing singular about it. Every vector can still be broken cleanly into components. You can still project. You can still calculate. The geometry works fine. It is just not the geometry of a schoolroom. So when we demand that the space of quantum states have all positive lengths, we are demanding something of the mathematics of quantum theory that we do not demand of the mathematics of spacetime itself. That is worth saying twice. The requirement that quantum states live in a Hilbert space is a stronger requirement than the one we impose on the fabric of the universe. The generalization, a space where lengths can be positive, negative, or zero, turns out to have been studied by mathematicians long ago. It is called a Krein space, after Mark Krein, a Soviet functional analyst who worked on differential operators. Krein's move was exactly the one we are describing. When you study the eigenvalues of an equation like Schrödinger's, you almost always assume from the outset that your space of functions is a Hilbert space, that everything has positive length. Krein said, "Let us drop that. Let us allow the negative norms and see what survives." And what he found is that a great deal survives, that you can still prove all kinds of things. And then this beautiful piece of mathematics sat in the literature for decades, essentially unused by physicists because nobody had a reason to reach for it. Turok's account of how it entered the story is almost mundane. His student Sam Bateman has a real appetite for the mathematical physics literature, and he was reading and searching, and the search tools we now have are very good at finding papers, and somewhere in that process he came across the notion of a Krein space, which was not generally known among physicists. That is it. That is how it happened. A generalization of the foundations of quantum theory was lying on a shelf, catalogued, waiting, and someone browsing found it. But here is the part of this that should genuinely surprise you, and it is the part that makes the whole proposal much less radical than it first appears. Physicists have been working in indefinite spaces this entire time, every day, routinely. Any modern calculation in gauge theory, which means any calculation in the theory of the strong force, or the electro-weak force, or anything else in the standard model, is done using a set of auxiliary objects introduced by Fadeev and Popov in a framework named after Bechy, Rouet, Storer, and Tyutin. Those auxiliary objects are also called ghosts. They live in exactly this kind of indefinite space, with positive and negative and null directions. Physicists have been computing with them since the 1960s and trusting the answers, and the answers keep matching experiments to absurd precision. This is not a fringe technique. This is how the standard model is computed. So why did nobody notice that the door was already open? Because of the last step. The standard prescription is that you work in the big indefinite space in order to respect more symmetry. That is the whole reason to go there. It makes the calculation cleaner and keeps the symmetries visible. And then, at the very end, you project. You perform an operation that selects out a physical subspace in which everything has positive length, and you declare that the physical subspace is where reality lives. Everything with a negative norm gets swept up and removed before anyone looks at the answer. The final object is an honest Hilbert space, and honor is satisfied. For 50 years, that final projection was the step nobody questioned. It was not a result. It was a habit, a very sensible habit, adopted for excellent reasons, which had never once been load-tested to see whether it was actually necessary. And the reason it was never load-tested is that in ordinary gauge theories it does not cost you anything. The ghosts there really are pure bookkeeping. Nothing is lost by removing them. It is only when you get to a theory where the negative norm states are genuinely part of the physical content, where you cannot remove them without removing something real, that the habit becomes an obstruction, which is precisely the case in four-derivative gravity. So the question Bateman and Turok set themselves is this. Can you build a quantum theory in a space with positive, negative, and null lengths, and never project at all, sum over everything, ghosts included, and still get sensible probabilities out? The answer, they say, is yes, and the price is one small modification to the rule that connects the mathematics of quantum theory to the numbers you actually measure. It is the rule that Born wrote down in 1926 and that every physicist since has treated as untouchable. And the modification is so slight that in ordinary quantum mechanics it changes nothing whatsoever. Part 8. A small change to the deepest rule. The rule we are about to modify is the joint where quantum mechanics touches the world, and I want you to appreciate how load-bearing it is before we go near it. Everything else in quantum theory is about how a wave-like mathematical object evolves. The equations are smooth and deterministic and beautiful, and they say nothing at all about probability. There is no randomness anywhere in them, and yet what we observe in the laboratory is a distribution of outcomes. This detector clicks sometimes, That one clicks other times, and the pattern is statistical. Something has to connect the smooth mathematics to the clicking. That something is a single line, written down by Max Born in 1926. To get the probability, take the amplitude and square its magnitude. That is the Born rule, and it is not derived from the rest of quantum mechanics. People have spent a century trying to derive it and arguing about whether they succeeded. It is bolted on. It is the one place where the formalism reaches out and makes contact with experience, and it works to the limit of every measurement we have ever made. So when someone proposes adjusting it, the correct initial reaction is suspicion. Mine was. But watch what the adjustment actually is, because it is not what you are expecting. Written out for a scattering process, the rule says, take the initial state, act on it with the operator that describes how the system evolves. Physicists call that operator the S matrix, the scattering matrix, and all it does is take a system from before to after. Then ask how much of the result lies along the final state you're interested in, and square the magnitude of that number. And hidden inside this, doing quiet and essential work, is normalization. The initial state has to be normalized. Its length has to be 1. Otherwise, the probabilities you get out do not add up to 1, and probabilities that do not add up to 1 are not probabilities. In a Crane space, you cannot normalize. There is nothing to divide by. The length might be negative. It might be exactly 0. The move that the entire rule depends on is unavailable. Here is the fix. Instead of a normalized state, use a projection. A projection is a simple thing, and you have already met it tonight. Given an arrow and a direction, projection asks, how much of this arrow points that way? That question has an answer whether or not the arrow has a sensible length. It does not require you to normalize anything, because you are not asking how big the arrow is, you are asking how it is oriented. So the construction goes like this, and I am going to say it slowly. You project onto the initial state. You evolve forward with the scattering matrix. You project onto the final state. You evolve back with the conjugate operator. And then you take the trace, which is a mathematical operation that means, in plain terms, sum over every state in the space. Every one, including the ghosts. Nothing is left out and nothing is thrown away. The number that comes out of that procedure is the probability. Now, the single most important thing about this, the thing that makes it a piece of physics rather than an act of desperation, is what happens when you apply it to ordinary quantum mechanics. Apply it to an electron in a magnetic field, or a photon at a beam splitter, or any of the 10,000 textbook problems, and it returns exactly the same numbers as the Born rule. Not approximately, exactly. It is a completely equivalent formulation of the rule we have always used. Born's version and this version are the same statement written 2 ways, in the same sense that a fraction and a decimal can be the same number, and that matters because nobody is proposing to change any prediction about anything anybody has ever measured. What is being proposed is that we had been using the special case of a more general statement and mistaking it for the whole. The general statement asks only about orientation. The special case, by dividing through by a length, quietly assumed the length was positive, and so quietly assumed the answer to the question of what kind of space quantum theory lives in. Let me put you inside it for a moment, because I think it is easier to feel than to follow. Imagine you're handed a space that works like the space-time you live in, where the interval between 2 things can come out positive, negative, or exactly 0. Someone gives you an arrow in that space and asks how long it is, and the question fails. Not because you lack a ruler, because the answer comes back negative, and there is no such thing as a length of -2. Every instinct you have about measuring things has run out of road. Now the same person asks a different question. Not how long is this arrow, but how much of it points along that direction over there. And you can answer. You slide the arrow flat against the direction, and there is a definite amount of it lying that way, and the strange signs in the space do not obstruct you at all. So you do it once. How much of this arrow points along where we started? Then you let the arrow evolve and you do it again. And then, instead of deciding which directions in the space are respectable, you go around the whole space and add up every direction there is. The good ones, the wrong-signed ones, the null ones lying exactly on the boundary. You sweep the entire space and you sum. And a number comes out. And the number is between 0 and 1. Nothing was removed. That is the thing to hold on to. In the old way, you had to purge the space of its bad directions before you were allowed to ask a question. In this way, you ask a question the space can actually answer, and then you count everything. Now, this does not work automatically. It works under a condition, and the condition is the actual content of the paper. The condition is a symmetry. Imagine an operator whose only job is to look at a state and report which kind it is. It returns +1 when handed a positive norm state, and -1 when handed a negative norm one. That is all it does. It is about as simple as an operator gets, and the requirement is that this operator be a symmetry of the theory, that the dynamics, the evolution, the scattering matrix all commute with it, so that the theory cannot tell the difference between running normally and running with all the ghost states flipped in sign. Bateman and Turok call it ghost parity, and their result is that if the theory has this symmetry, then the probabilities constructed by the projection method are always positive, and they always sum to 1. Not sometimes, not approximately. The positivity is a theorem, given the symmetry. The word hidden in the title of their paper, Escape from Ostrogradsky via Hidden Ghost Parity, refers to the fact that you cannot see this symmetry in the four-derivative theory when it is written down the ordinary way. It is not staring at you. It becomes visible when you rewrite the theory in a different but equivalent form, as an ordinary two-derivative theory of two fields, with a symmetry between them that mathematicians label O1,1, and that label tells you something lovely. 1,1 means a space with 1 plus sign and 1 minus sign, the smallest possible version of exactly the structure we have been discussing, the structure of time and one direction of space. The symmetry that rescues the theory turns out to be, in the simplest possible setting, the same kind of symmetry that relates time to space in relativity. So the ghosts are not exercised, they are enrolled. You sum over them along with everything else, and the reason the answers come out sane is not that you remove the offending states, but that the theory possesses a symmetry which makes their contributions organize themselves. One consequence is worth flagging, because it sounds more radical than it is. In this construction, the amplitude, the thing you use to square, is explicitly not a physical quantity. You're not allowed to think of it as one, but pause on that, because it was already true. In ordinary quantum mechanics, the amplitude has never been observable. You always had to square it before it meant anything. All that is happening here is that a step which was always mathematical scaffolding stops being treated as though it were a stage in a physical process. Now I have to give you the boundary of the claim, precisely, because this is exactly the place where popular accounts of physics go wrong. What the paper claims to establish is that the theory is a four-derivative, ultraviolet complete quantum field theory with a consistent perturbative expansion, that the quantization can be done covariantly, respecting the symmetries of space-time, that causality and unitarity, in the technical form called the optical theorem, hold to all orders in perturbation theory, and that all transition probabilities are positive at tree level. Tree level. That phrase is doing real work, and I am not going to slide past it. In quantum field theory, tree level means the simplest class of processes, the ones without loops in them. Loops are where the infinities live, where the subtleties live, where a great many hopeful results have died over the last century. Positivity at tree level is a genuine and non-trivial theorem. It is not positivity in general. The authors know this and say so. Anyone telling you the ghost problem is now closed has read the headline and not the abstract. There is also a rival route to the same destination, and honesty requires it. Carl Bender has spent years studying quantum systems whose energy appears to have no flaw and which nevertheless turn out to have entirely positive energies when analysed correctly. His classic example being a potential shaped like minus the fourth power of position, which looks like a catastrophe and behaves itself once the calculation is deformed into the complex plane. Philip Mannheim has pursued the other half of the quadratic gravity action, the Weyl piece, as a candidate fundamental theory in its own right, on the grounds that it has more symmetry and contains no length scale at all, and has argued it could account for the rotation curves of galaxies without dark matter. Turok's objection to their method is specific rather than dismissive. Their approach, as he characterizes it, amounts to redefining the inner product, inserting a minus sign by hand whenever two negative norm states meet, and his claim is that doing so is not covariant. It picks out a preferred frame of reference. In quantum mechanics, where you can get away with a fixed notion of time, that may be survivable. In field theory, where the theory must respect the freedom to rotate, to move, to change velocity, a brute force change to the inner product will break exactly those symmetries. His claim is that the ghost parity construction is the only resolution that fully respects them. He adds that the groups talk collegially, that Mannheim will undoubtedly think the Edinburgh framework fails for reasons of his own, and that all criticism is welcome. Which is a reminder. This is not a verdict. It is a live disagreement among people circling the same problem. But look at what has happened twice now. The classical objection dissolved when someone noticed it was describing the expansion of the universe rather than a catastrophe. The quantum objection dissolves, if it dissolves, when someone notices that a negative norm is a property of a label rather than a property of a probability. Two of the most durable roadblocks in the field, and in both cases the disaster was in the description, not in the world. Which leaves the obvious question, and it is the one that separates the honest version of this story from the inflated one. If both objections are gone, what exactly is sitting on the table? Because the answer is not everything. Part 9. What was actually solved? Now we come to the part of the story where most retellings go wrong, and I want to get it right, because the boundary of this claim is more interesting than the claim. Remember that the theory has two curvature-squared terms, and that the symmetries of general relativity permit exactly two. One is built from the Ricci scalar, the piece of the curvature that tracks how volumes get distorted. The other is built from the Weyl tensor, the piece that tracks how shapes get distorted while volumes stay the same. If you have ever seen an image of gravitational lensing, where a distant galaxy appears smeared into an arc, you have seen Weyl curvature doing its work. It is the shearing part. It is also, in this theory, where all the trouble lives, because the Weyl term is what brings the graviton-like excitation, a vector mode, and the spin-2 ghost. The Ricci part brings the scalar, the sweet little scalar, the local scale of the metric, and what Bateman and Turok have in hand is a limit of the theory. You take the coupling in front of the Weyl term and you set it to 0. And when you do that, the entire Weyl sector decouples and goes trivial. The graviton, the vector, the spin-2 ghost, all of them simply drop out of the physics. What is left is a single degree of freedom describing the local scale of the metric, and that theory is renormalizable, asymptotically free, and yields positive probabilities. That is the result. That is what we understand quantum gravity in a certain limit means. Now let me tell you what that limit does not contain, and I want to be blunt, because Turok is blunt about it. It has no gravitons, it has no gravitational waves, so it cannot describe the ripples that were detected coming from merging black holes, arguably the most beautiful measurement of the last 20 years. It is not, in Turok's own phrasing, the real world. It is not the right theory of gravity. It is a limit of something that might be the right theory of gravity. What it is a toy model. And I do not want that phrase to land as a deflation, because in theoretical physics, a good toy model is not a consolation prize. It is the instrument you use when the real thing is out of reach. It is fine for describing cosmology, because cosmology is largely about the overall scale of space, which is precisely the degree of freedom this theory keeps. It even admits black hole-like solutions, which means you can ask questions about horizons in a setting where you actually control the mathematics. Nobody has been able to do that before with a quantum theory that is complete at short distances. It is also complete in the specific technical sense that quantum chromodynamics is believed to be complete. It has a genuine continuum limit. It does not fall apart if you zoom in without limit, and it does not need to be rescued by strings or by anything else. It is self-contained. The infrared, though, is a different country. Asymptotic freedom means weak coupling at short distances, but it comes with a mirror image consequence at large distances, where the coupling grows strong. This pairing is sometimes called asymptotic freedom in the ultraviolet and slavery in the infrared, and the strong nuclear force is the classic example. At short range, quarks and gluons barely notice each other. At long range, they cannot be separated at all. You cannot pull a single gluon out of a proton and put it on a table, because the force required to separate it creates new particles out of the vacuum faster than you can pull. The only things that actually exist as free objects are composites, protons, neutrons, and in principle objects made purely of glue, called glue balls. Turok's expectation is that his scalar theory has the same structure. Weakly coupled and simple at short distances, strongly coupled and complicated at long ones, and perfectly well defined at both ends. Which raises the obvious question: what are the physical objects in the strongly coupled regime? What is the glue ball of this theory? Nobody knows. Nobody has computed it. Turok says a student is putting the theory on a lattice to find out, and I want to underline how unusual that sentence is. Almost nothing in the quantum gravity conversation can be simulated. You cannot put string theory on a computer and ask it what happens. There is no complete formulation to put there. Here, you can. Whatever this theory is, it is the kind of thing you can hand to a supercomputer and interrogate. And then there is the word I promised not to slide past: tree level. The positivity result, the proof that all the probabilities come out positive despite the ghosts, is established at tree level, meaning for the simplest class of processes, the ones without quantum loops. Loops are where the infinities live. Loops are where a great many hopeful results in the history of this subject have quietly died. The paper's other claims about causality and unitarity are stated to all orders, but the positivity of transition probabilities is a tree-level theorem. That is a real result, and it is not the whole building. So the honest summary is this: in a limit with no gravitons, for the simplest class of processes, a four-derivative theory has been quantized without removing its ghosts and without producing nonsense. Everything else is future work: the loops, the Weyl sector, the coupling to actual matter, and the question of whether any of it survives contact with the real world. It is worth knowing that this is not one group working alone. There is a genuine revival underway, and it has been going for over a decade. John Donoghue and Gabriel Menezes, now at São Paulo, found that in simple scenarios the ghosts do not do the damage everyone feared. They are so unstable that they vanish before they can inflame the vacuum or generate negative probabilities. Donoghue's own summary is that things everyone else would have said violated unitarity do not seem to. Damiano Anselmi at Pisa found that you can sidestep the problems by using alternative versions of Feynman's rules for calculating quantum events, and his comment on the sociology is perfect. You have the impression that the last word had been said, and it was just not true. Alberto Salvio and Bob Holdom independently noticed that the final step in the probability calculation can be adjusted so that probabilities always stay positive, which is in spirit the neighbourhood the Edinburgh result lives in, arrived at by a different road. Luca Buoninfante at Radboud, whose calculations helped shore up the older theory, says that so far there is no hint telling us we should throw quantum field theory away, and that when you apply the standard framework to gravity, you do not only get a unique theory, you also get new predictions, and there is a bill attached to all of this, which Donoghue is careful about. If the ghosts are allowed to exist, something has to give, and what gives is not stability and not unitarity. It is the strict ordering of cause and effect. That minus sign lets a ghost briefly skip backward in time, influencing particles it otherwise could not. In this picture, the forward flow of time you experience is not a fundamental law, but a delicate average over enormous numbers of temporally squishy micro-moments. Cause and effect hold at your scale because almost everything cancels. Underneath, occasionally, effects sneak ahead of their causes. Whether that is an acceptable price is exactly where the disagreement lives. Alessia Platania at Copenhagen, who works on a different approach to quantum gravity, supplies the necessary caution. One does not simply tinker with critical tenets of physics like causality and unitarity. Her verdict on whether these fixes address all the potential problems is that it is still open as a question. Benjamin Knorr at Heidelberg, also working elsewhere, allows more mildly that there is something to understand there. That is the state of play, not a solved problem, a previously abandoned building with scaffolding on it, and a number of competent people arguing on the pavement about whether it is safe to go inside. Which brings us back to Stell's question, and I told you it would change meaning. Do you like it? Because here is the thing about the theory sitting on the table tonight. It is the same theory, not a modification of it, not a descendant, not something inspired by it. The same action, the same two terms, the same absence of any freedom to choose. Nothing about the mathematics of 1977 has been altered. Every single thing that has changed is on our side of the equation. What we are willing to allow, which spaces we consider legitimate, which final steps we regard as mandatory. If the theory is likable now and was not likable then, and the theory has not moved, then the thing that moved is us, which means that for 50 years taste was doing the work of proof, and that is a much more uncomfortable thought than any ghost. There is one more thread to pull, and it explains something that should have been bothering you. Why was it a cosmologist standing in front of this door? Turok is not a specialist in the quantization of field theories. He says so himself cheerfully, that he is not a sophisticated mathematician and spent his career computing things about the early universe. So how does a man who studies the beginning of the universe end up rescuing a theorem-haunted theory of gravity from the 1970s? because he did not come to four derivative fields through quantum gravity at all. He came to them by looking up. Part 10. The sky was already showing us. You have seen this image, even if you do not know its name. It is an oval, mottled in false colour, blue and red and yellow blotches distributed across it like a weather map of nowhere. It appears in every documentary about the beginning of the universe. It is on posters. It has been on a postage stamp. What it is a photograph of the sky in microwaves, and what it shows is the temperature of the oldest light there is. When the universe was very young, it was a hot plasma, opaque, glowing, and then it cooled enough for light to travel freely, and that light has been travelling ever since. It surrounds us. It arrives from every direction, and it is almost perfectly uniform in temperature, but not quite. There are fluctuations, tiny ones, differences of a few parts in 100,000, hot patches and cold patches spread across the whole sky. Those fluctuations are the most important pattern in cosmology, because they are the seeds. Slightly denser regions pulled in more material and became more dense, and eventually became galaxies, which became stars, which became the carbon and oxygen and iron that you are partly made of. When Turok describes those fluctuations as our ancestors, he is not being poetic. That mottled oval is a family portrait. So the natural question is what made them, and the standard answer for 40 years has been inflation, a brief episode of ferocious expansion in the first fraction of a second, during which microscopic quantum fluctuations were stretched to the size of the visible universe. Turok does not have inflation in his picture, which means he cannot stretch anything. So he took a different approach, and this is the move that eventually led him to a 1977 theory of gravity. He asked a simpler question. Never mind what stretched them. Just look at the pattern and ask what kind of quantum field it looks like. The answer is partly comfortable and partly not. Statistically, the fluctuations look exactly like the vacuum fluctuations of a quantum field. They have the character of Gaussian random noise, which is what quantum vacuum fluctuations look like. Good. But their spectrum is wrong. The spectrum tells you how the strength of the fluctuations varies with wavelength, with scale, and the observed spectrum is redder than an ordinary field would produce. Redder means more power on the large scales. The big, gentle, sky-spanning variations are stronger relative to the small ones than they ought to be. And Turok's claim is that this is not a mystery requiring a story. It is a signature. The pattern in the sky looks exactly like a four-derivative field. Ask what sort of quantum fluctuating field the sky resembles, and in his words there is no question about the answer. Now put that beside everything we have spent tonight on. The thing quantum gravity appears to require is a four-derivative field. The thing printed across the sky appears to be a four-derivative field. If both of those are right, then they are the same thing, and the conclusion is one of the more remarkable sentences available in modern physics. The pattern of temperature variations covering the sky is a photograph of quantum gravity fluctuating. I want to give that its full weight before I take some of it away. The standing objection to quantum gravity, for as long as there has been quantum gravity, is that it cannot be tested. The energies involved are so far beyond any conceivable accelerator that people reach for comparisons involving machines the size of galaxies. That is the reason the field has spent 50 years arguing about mathematics rather than looking at data. And the possibility on the table here is that the experiment already ran. It ran before there were atoms, before there was anything to be made of matter, and its output has been hanging above your head your entire life, in a pattern that was mapped in fine detail by satellites decades ago, and has been reproduced on the covers of textbooks ever since. Not a future experiment requiring a machine we cannot build. A finished measurement, in an archive, waiting for someone to read it correctly. And now the part that has to come immediately, because this is the most contested claim in the whole story. There is a published critique, a paper titled Pathologies of Dimension Zero Scalar Fields by James Klein and Anna Maria Hell, disputes the claim that scalar fields of this kind can do the cosmological work Turok's earlier papers assigned to them. Their argument is that the spectrum of the theory contains a ghost, that this leads to classical instabilities and a quantum violation of unitarity, that the new scalars therefore cannot cancel the standard model's contributions to the cosmological constant without introducing exactly the pathology everyone was worried about, and that coupling such fields to ordinary matter would generate a confining fifth force, which observation rules out. Turok's response has two parts, and he gave it as a referee, which he says openly. First, he argues the critique addresses a different object. His group used these four derivative fields as quantum fields, fluctuating on a fixed curved background, in order to study whether the energy carried by quantum fields makes sense, given that such energy comes out infinite even on a fixed background. Klein and Hell, on his reading, took that same field content and treated it as though it were the gravitational action itself, and then discovered it does not make a good theory of gravity, which, he says, is beside the point, because that is not what it was built to do. Second, he says the critique repeats the folklore that negative norm states are inadmissible, which is precisely the assumption the newer work rejects, and that the critics had not seen the newer work when they wrote. You should hear all of that as an interested party's account of an unresolved dispute, because that is what it is. Turok is one of the two sides. He also says he found their paper not clearly enough written to determine whether their analysis is correct, which is the sort of remark that tells you the temperature of the exchange. I am not going to tell you who is right. Nobody currently knows who is right. That is what an open question in physics actually looks like from the inside, and it is much less tidy than the version that reaches the public. But suppose for a moment that the sky is not even the biggest consequence here, because it is not. The biggest consequence has nothing to do with gravity at all. Part 11. The Assumption. Nobody wrote down. Let me ask you a question that sounds like a history question, and is actually the most important question of the night. Why did anyone ever believe that quantum gravity requires strings in 10 dimensions? Not whether it does. Why anyone believed it? Because that belief has shaped the careers of thousands of physicists, absorbed billions in funding, filled bookshelves, and reorganized entire university departments. And beliefs that large are usually built on arguments, and arguments have premises, and premises can be listed. Turok lists 3. The first premise is that the allowed theories have only 2 derivatives in the action. When strings were quantized, 4 derivative theories were not on the table. They had already been ruled out, by Ostrogradsky, by the ghost folklore, by the accumulated sense that this direction was closed. So the entire construction was carried out inside a space of possibilities from which the simplest candidate had already been removed. The second premise, and Turok considers this the strongest, is that the theory can only be constructed in perturbation theory. What he means is that string theory has no complete formulation. There is no principle from which the full nonlinear theory follows, the way the whole of general relativity follows from the principle that physics should look the same to everyone. Einstein wrote down a principle and the theory came out. String theory is constructed by demanding a list of properties: relativistic invariance, unitarity, positive probabilities, and building outward term by term in an expansion. That is a very different kind of object. It is a recipe rather than a law. The third premise is that the theory lives in a Hilbert space, all state norms positive. Now notice something about that third one. It never looked like a premise. Nobody wrote it at the top of the page as an assumption to be justified, because it did not feel like an assumption. It felt like a definition. It felt like part of what the words quantum theory mean. And this is the thing about the assumptions that do the most work in a mature science. They are invisible precisely because everyone shares them. A premise that somebody disputes gets examined. A premise that nobody disputes gets absorbed into the vocabulary and stops being visible as a choice at all. And what Bateman and Turok now have, if their result stands, is a counterexample. A specific, written-down, ultraviolet complete quantum field theory, self-contained in the way the strong force is believed to be self-contained, with causality and unitarity intact, which does not live in a Hilbert space. It lives in something more like the space-time we inhabit, positive directions, negative directions, and null directions along the boundary. Turok's own reaction to this is worth reproducing exactly, because he does not hedge it. Now that we have seen you do not need that assumption, the whole thing has no basis. And here I have to slow you down, because that sentence is stronger than the evidence and Turok knows it. He adds the qualifier himself, that this is what they think is true, that they have an example. So let me say precisely what has and has not happened to string theory tonight. Nothing has disproven string theory. Nothing in this work says the world is not made of strings. What has been challenged is a claim of necessity. There is a difference between the sentence gravity might be made of strings and the sentence gravity must be made of strings, and the second one is what has been under pressure. For decades, the argument for the elaborate approach was not that it had been confirmed, but that there was no alternative, that the simple route was mathematically closed, so the elaborate route was forced. If the simple route is open, then the elaborate route is one option among at least two, and options have to compete on evidence rather than on uniqueness. That is a smaller claim than a refutation, and, in the actual practice of science, a more dangerous one. Which brings me back to that unicorn. Earlier we said that a negative norm state is like a red dancing unicorn in your equations, unobservable, therefore harmless, therefore not worth losing a theory over. That was a defense of the ghosts. But turn it around and look at the other side of the field, because extra dimensions are also unobservable. Nobody has seen a curled-up seventh dimension. Nobody has seen a superpartner particle. The Large Hadron Collider looked hard and found none. Nobody has observed another branch of the wave function. Those are all unicorns too. The difference is not observability. The difference is obligation. The ghost is tolerated. The theory contains it. Nothing measurable depends on it, and you sum over it and move on. The extra dimensions are required. The framework does not work without them, and you must believe in 6 or 7 of them to hold the rest of it up. And a unicorn you're obliged to feed is a very different animal from a unicorn that happens to be standing in the room. Now let us follow the same audit somewhere much larger, because Turok does. If one unexamined premise was holding up the conclusion that we need 10 dimensions, what about the premises holding up the multiverse? And I want to steelman the other side first, properly, because they are not fools, and they are not motivated by a love of complexity. A string theorist would tell you that they also care about simplicity, that string theory grows from extremely minimal starting assumptions, and the elaborate structure is an output rather than an input. A many-worlds advocate would tell you that their position is the austere one, ordinary quantum mechanics with a postulate removed, no collapse, no special role for measurement, just the equation taken literally everywhere. The branching universes are not something they wanted. They are a consequence they accept because the alternative is to add machinery. Both camps would say, with justification, that they are the ones shaving with the razor. Turok's answer to that is not that they are insincere. It is that whatever the intent, the output is the most complex object anyone has ever proposed. And when a chain of minimal-looking assumptions delivers an infinity of unobservable universes, the responsible move is to go back and audit the assumptions, carefully, one at a time, including the ones nobody thought to write down. And one of those, in both cases, is that a consistent quantum theory must live in a Hilbert space. Then he raises something harder, and this part is a genuine technical problem rather than a matter of taste. It is called the measure problem. Inflation, in most versions, does not happen once. It keeps happening in different regions, producing what Alan Guth calls pocket universes, and each pocket can be infinite in extent. So if you want to predict anything at all, you have to ask what a typical observer sees, which means you need a way of weighting the possibilities. You need a measure on an infinite space of outcomes. Turok tells a story about this. When multiverse ideas started gaining ground in particle physics, he and others began worrying about exactly this problem, and a friend of his who knew John Nash, the mathematician most people know from the film about his life, and one of the deepest thinkers about mathematical structure in the 20th century, went and asked him, "Can you define a measure on an infinite space?" And Nash's answer, as Turok relays it, was no, ridiculous, no chance. I will flag that as an anecdote rather than a theorem because that is what it is. But the underlying point stands on its own and is widely acknowledged even by people inside the program. Unless some special symmetry guides you, a theory that generates a randomly infinite space is not a predictive theory. If everything happens somewhere and you cannot say how often, you have not explained anything. You have described a lottery with no odds. Turok suspects the many worlds picture inherits the same defect, that nobody is ever going to be able to quantify probabilities in it properly. That suspicion is contested, and people have written serious work attempting to derive exactly those probabilities. But the objection is not frivolous. So what does he offer instead? This is the part I find most beautiful, and it comes from Stephen Hawking. Hawking took the idea of entropy, the quantity that explains why the air in a room spreads out evenly rather than bunching in a corner, and worked out how to define it for space-time itself. That is where black hole entropy comes from. Turok and Latham Boyle extended the same method from black holes to whole universes. You can assign an entropy to a cosmology, and therefore ask which cosmology has the largest number of microscopic states, and the answer is ours. Using Hawking's definition, The universe with the greatest number of microstates is smooth, homogeneous, isotropic, spatially flat, and carries a small positive cosmological constant. The published version of the statement is that gravitational entropy is largest for universes which are spatially flat. Think about what that does to the traditional framing. Cosmology has spent decades treating the smoothness of the universe as a puzzle about initial conditions. Somebody must have set it up in an extraordinarily special state, and inflation is the dynamical machinery invoked to smooth out a random start, because two patches of the early sky that were never in causal contact somehow have the same temperature. That is the horizon problem, and it is a real problem if you think the smoothness had to be achieved. But the air in your room did not have to be smoothed by anything. Nobody stirred it. It is evenly distributed because evenly distributed is what almost every possible arrangement of those molecules looks like. Smooth is not an achievement. Smooth is typical. Turok's proposal is that the universe is the same. You do not need dynamics to reach a typical configuration. You need a way of counting. Quantize, count the states consistent with the large-scale properties, and pick one at random, and the one you pick will look like a smooth, flat, gently accelerating universe, which is the one you are in. There is something quietly consoling in that, and also something that removes a story people are fond of. Nobody arranged this. No initial condition had to be chosen with care. No dial had to be set. The universe you live in requires no author, because it is what almost any universe of this kind would look like. That is a stranger kind of comfort than being special, and I think it is a better one. The audit has one more prize, though, because there is a number in physics that has embarrassed the field for 40 years, that everybody agrees is unexplained, and that this picture may explain for free. Part 12. A number. Nobody had to tune. Physics has three numbers that sit in the same universe and do not appear to belong to the same universe. The first is the Planck mass, the scale at which gravity becomes as strong as the other forces, and it comes out at roughly 10 to the 19th power giga-electron volts. The second is the weak scale, the energy at which the weak nuclear force does its business, and the Higgs field lives, and that is about 100 giga-electron volts. The third is the scale of strong nuclear physics, which sits at a fraction of a single giga-electron volt. And then, far below all of them, there is the cosmological constant, which corresponds to an energy of about a milli-electron volt. Numbers like that are hard to feel, so let me put the first two side by side differently. The gap between the weak scale and the Planck scale is a factor of roughly 10,000 million. If the weak scale were the width of a human hair, the Planck scale would be measured in light years. These are not neighbouring quantities that happen to differ. They are separated by an absence so large that physicists gave the absence a name. It is called the hierarchy problem, and the awkward truth is that in the standard model the smallness of the Higgs mass relative to the Planck mass is not explained. It is fitted. You pick the numbers so that the theory matches what the accelerators see, and there is no principle telling you why they should differ by that particular enormous amount. This is the single most discussed unexplained number in particle physics, and it is the reason supersymmetry was so attractive for so long. It offered a mechanism that would hold the two scales apart naturally. Then the Large Hadron Collider looked for the superpartners and did not find them, and the problem came back untouched. There is a reason physicists find unexplained numbers intolerable rather than merely untidy, and it is not fussiness. An unexplained number is a place where the theory is quietly being told the answer. Every fitted parameter is a small admission that something upstream is missing, and the bigger the fit, the louder the admission. A factor of 10,000 million put in by hand is not a rounding error in the bookkeeping. It is a signpost saying that whatever generates the masses of things is not in the theory yet. Here is the mechanism this picture offers instead, and it is almost aggravating in its simplicity. Coupling constants, the numbers measuring how strongly things interact, are not fixed. They change with the energy at which you probe. Physicists say the coupling runs, but the running is logarithmic, which is to say astonishingly slow. You can change the energy by a factor of 10, and the coupling barely moves. Now, take a theory that is asymptotically free, so the coupling is weak at high energies and grows as you come down. Define it at some very high energy, say the Planck scale, and give it a modest value, something like a tenth. Then walk downward in energy and ask where it becomes strong, and because the running is logarithmic, the answer is not a little bit lower, it is exponentially lower. You get an enormous separation of scales out of a perfectly ordinary starting number, automatically, unavoidably, without anyone tuning anything. And we know this works, because nature already does it. The coupling of the strong nuclear force is something like a 30th at the Planck scale. Follow it down and it becomes strong at around 1 giga-electron-volt, which is where protons and neutrons live, which is to say, where you live, since it sets the mass of essentially all ordinary matter. The scale of everything you're made of is exponentially far below the Planck scale, and no physicist calls that fine-tuning. Nobody thinks the proton's mass is a suspicious coincidence. It comes out of slow logarithmic running from a modest number, and it is the least mysterious thing in the world. So Turok's hope is straightforward. If the Higgs is made out of this scalar, the sweet little scalar, the one that carries the local scale of the metric, then the Higgs mass being exponentially below the Planck mass is not a coincidence requiring explanation. It is what that mechanism does, and as a bonus, it would tie the Higgs mechanism to gravity, rather than leaving them as two unrelated pieces of furniture in the same room. Which brings us to the sentence that should stop you. In this picture, the Higgs boson is not fundamental. There are two solid reasons that is not a wild thing to say. The first is that the Higgs sector is not ultraviolet complete. Follow its self-coupling up in energy, and it runs to a pole at a finite scale. It blows up, and the theory stops making sense. That is a known structural defect, not a rumour. The new scalar, by contrast, is complete. So you have an incomplete thing and a complete thing with similar character, which is precisely the situation in which physicists have historically found that the incomplete thing was made of the complete thing. The second reason is the original inspiration. The Higgs mechanism was not invented from nothing. It was borrowed from superconductivity. Philip Anderson had built a model of what happens inside a superconductor, where a condensing scalar field expels magnetic fields and gives the photon an effective mass within the material. And the field doing that job in a superconductor is not fundamental at all. It is made of pairs of electrons, the Cooper condensate. The very object the Higgs was modelled on is composite. Now let me take you back to the early 1960s, because this story has happened in this building before. It is Edinburgh, and there is a notoriously shy theoretical physicist working on an idea he has taken from superconductivity and dragged into particle physics. There is no experimental evidence for it. None. He is proposing a field that fills all of space and gives mass to particles by interacting with them, and he is doing it on the strength of an analogy with the behaviour of metals at low temperature, and he is told that it is nonsense, not gently. The objection is technical, and it sounds devastating. His model violates cluster decomposition. Cluster decomposition is the assumption that things far apart are uncorrelated, that whatever is happening here does not know about what is happening there, if there is far enough away. It is about as intuitive as an assumption gets, and it had been treated as one of the basic requirements of a sensible quantum field theory. And Higgs's model breaks it flagrantly. It says the vacuum is full of a condensate whose value here is exactly its value there and everywhere forever. Perfectly correlated across the entire universe. His colleagues found it shocking, and they said so, and they told him he was applying classical notions inside a quantum field theory where they did not belong. He was right. The assumption was wrong. It took until 2012, nearly 50 years, for a machine to be built that could see the particle, and when it was seen it was where he said it would be. I am not going to draw the parallel for you. You can see the shape of it. There is one detail I cannot resist, though. The chair Turok holds at Edinburgh is the Higgs chair, named for that same physicist. And it is from that chair that the suggestion is now being made that the Higgs boson may not be fundamental. When this was pointed out to him, why do they still give you the Higgs chair if you're saying the Higgs is not fundamental? His answer was that Peter Higgs would have been the last person on Earth to insist his boson was fundamental. The thing that condenses in a superconductor is not fundamental. Higgs knew that better than anyone because it was where he got the idea, which leaves exactly one thing left to settle. The question we started with, that I have been carrying all night without answering. Part 13, have we just solved quantum gravity? We have arrived at the question, so let me put it to you exactly as the night began. Have we just solved quantum gravity? The answer is no. I want to answer that flatly and early, because you have given me most of an evening and you deserve better than a tease. We have not solved quantum gravity. We are not on the verge of solving quantum gravity. The people who did this work say so themselves in plain language unprompted. Turok's own summary is that they have not solved it yet but are halfway there, and then, in the same breath, that halfway is an optimistic way of putting it. Let me list what has not been done, because the list is long and every item on it is real. There are no gravitons in the theory that has been quantized. There are no gravitational waves in it, which means it cannot describe the signals that have been detected from merging black holes. The positivity of probabilities is proven at tree level, not for the loop processes where the infinities live. The whale sector, the half of the action containing the graviton, the vector mode, and the spin-2 ghost, has not been touched at all. The full theory remains unquantized. There is no experiment. The nearest thing to a prediction is a statement about primordial gravitational waves too faint for current telescopes, which might be reachable by the next generation of observatories, or might not. The reading of the microwave sky that started the whole enterprise is under published criticism, and that criticism has not been resolved. And there is an internal tension that Turok volunteers without being asked. His cosmological work needed 36 of these fields to make the arithmetic of the standard model close, while the gravitational work involves one, and he does not know how to reconcile the two. His words are that they do not yet know how to square that circle. So that is the debit column, and it is substantial. Here is what did happen, and I would like to argue that it is a stranger kind of news than a solution would have been. A theorem from 1850 and an axiom from 1926 both stopped being proofs. That is it. That is the achievement. Nobody discovered a new particle or a new force or a new dimension. Somebody noticed that an argument everyone believed was closing a door was doing something weaker than that. The classical objection turned out to be a description of cosmic expansion in frightening language. The quantum objection turned out to rest on the unexamined assumption that quantum states must live in a space where all lengths are positive, an assumption stronger than the one we make of spacetime itself, and one that nobody had ever load-tested because it did not look like an assumption. And the reason the removal of a proof is a bigger event than it sounds is what is behind the door. Behind that door is the only known way to write a local, four-dimensional, renormalizable, asymptotically free quantum theory of gravity that requires adding absolutely nothing to the universe. No strings, no extra dimensions, no superpartners, no landscape, just space-time, with the next obvious term included in the equation, in the 4 dimensions you can see. If any of that is right, then the thing everyone has been searching for since the 1930s was written down in 1977 and abandoned on grounds we can no longer defend. Do you like it? That was Stell's question about his own theory, and it turns out to have been the only question that mattered for 50 years. Not whether the theory was consistent, whether we could stomach what it asked us to accept, and I think that is the part worth sitting with, because it inverts the usual story about how physics gets stuck. We tend to imagine the field as blocked by things it cannot compute, problems too hard, machines too small, mathematics not yet invented. That is sometimes true. But this was not that. Every ingredient needed to reopen this question has been publicly available since the 1960s. The theory was published. The mathematics of indefinite spaces was catalogued and sitting on a library shelf. The projection reformulation of the probability rule is elementary once you see it, and physicists were already computing with negative norm states every working day. Nothing was missing. What was missing was somebody willing to ask whether the last line of a familiar calculation was optional, and to keep asking for 4 years after everyone sensible had concluded that it was not. The honest state of things now is a question, and Turok states it as clearly as anyone could want. Does a symmetry like ghost parity exist in the full theory, once the whale sector is switched back on? If it does, he says, this will be a complete theory of quantum gravity. If it does not, the trick may not generalize and the wall is still standing. He does not know. Nobody knows. That is the actual frontier, and it is currently occupied by a small number of people, some of whom think the whole approach is misguided, all of whom are publishing. And I want to leave you with the human version, because the human version is what this looked like from the inside. A student took a problem his supervisor privately believed was unsolvable. He spent 4 years on it and produced nothing publishable. 4 years of reading a difficult literature, working through the attempts of people like Bender and Mannheim, finding that none of them quite worked, and having nothing to show anyone. He taught himself covariant quantization of field theory out of enormous, rigorous textbooks that, by his supervisor's estimate, almost nobody currently practicing has ever opened, because they are too heavy in every sense. His funding ran out. He concluded he would not get a job in physics and made peace with it. And then in September, with nothing left to lose, it came together, and what it took was a slight tweak of the Born rule. He was later offered a position at a major research centre with no papers to his name, because a visiting expert in exactly the relevant kind of field theory heard him give an informal talk and understood what he was looking at. His supervisor's comment on the whole sequence is the least romantic and most accurate thing anyone has said about scientific progress, that this is the way it should work, and that all the chasing of papers is beside the point, and that Sam was doing it because he liked doing it. That is what progress actually looks like from the inside, not an announcement. 4 years of silence, a small change to a rule everyone thought was untouchable, and a question that is still open. So let me give you the shape of the whole night in one sentence, and then let you go. Twice tonight, an obstacle that had stopped physics for generations turned out to be a feature of the way we were describing things rather than a feature of the universe. The runaway instability was cosmic expansion. The forbidden negative norm was a property of a label nobody can measure. In both cases, the disaster was in the description, not in the world, and if that happened twice, in the same theory, to the two most durable objections in the field, then the question I would actually like you to carry away is not whether we have just solved quantum gravity. We have not, and I have told you why. The question is how many other things we currently call impossible are facts about our vocabulary. Because there is no procedure for finding out. There is no test you can run on your own assumptions to see which ones are load-bearing and which ones are habits. Every generation of physicists has believed it was working with a complete list of its own premises, and every single generation has been wrong about that in some way that only the next one could see, which means the present list is wrong too somewhere, and nobody alive knows where. The only practice available, and Turok says this is what he wishes he had understood at 20 rather than at 70, is to take each step you have never questioned and ask whether it is genuinely necessary, or whether it is simply what everyone around you has always done. There is a thought he offers near the end of all this that I keep returning to. The universe, he points out, is astonishingly simple at the very smallest scales and at the very largest. Atoms are simple. Black holes are almost absurdly simple. A mass, a spin, a charge, and nothing else. No more complicated than a single particle. The universe as a whole, on the larger scales, is described by a handful of numbers. All the complexity, all of it, lives in a narrow band in the middle, at roughly the size of a person. Which means the complicated thing in this story is not the universe, it is us. We are the tangled, improbable, unnecessary structure that formed in the thin zone between the simple and the simple, and for reasons nobody has ever explained, we turn out to be the part of it that can ask what the rest is made of. Tonight we watched a young man with no money and no papers move a wall that had stood since before his great-great-grandparents were born by changing one line of arithmetic. The universe has not told us yet whether he is right, but it has never stopped letting us ask.